She came and said, this isn't what I thought it was going to be. Okay, it's going to come up now. Okay, we are going to start with electricity and magnetism as soon as we finish Rachel's question.
Can you answer one of the questions on the board?
Absolutely.
E16B.
For something 16B. Okay. B. Okay, you're going to have to walk me through it because I don't remember the problems.
Okay, it says a toaster draws a current of 5 amps when it is connected to its 110 volt AC.
So I have a resistor draws a current of 5 amps when it's connected to what?
110 volt.
Okay, then what?
The question is, what is the resistance of the heating element?
So we have the voltage from the supply is 110 volts, which means that the 110 volts is also the voltage across the resistor because it's the only thing connected there. So we know the voltage and we know the current. We want to find the resistance. How to relate voltage and current? And resistance?
So we just find the resistance?
Yep. Or as Ohm's third law would say, R is equal to V over I. And of course, there is no such thing as Ohm's third law. It's just making fun of that. And so you just put your 110 volts over 5 amperes. And hopefully we can all come up with 22 there.
Okay, and that's because I was kind of confused on the wording of it. The heating element.
Okay, so we're good?
Yeah, we're good.
Excellent. All right, we're going to talk about magnetism. And after just 1 or 2 slides, Elette is going to come up and wow us with some amazing magnetic things. So just a little introduction before she comes up and shows off all of her things she has learned to show off. We're actually a lot more used to seeing magnets in action than we are seeing electricity in action because we have things like magnets for speakers, and horseshoe magnets, bar magnets, and those magnets that are right beside Rachel. Rack magnets that somebody left in the drawer. I think they left. And all these little magnets that we can play with. So we're used to seeing magnets and how they interact with them. We got them on the refrigerator for crying out loud. How do you suppose magnets were discovered? Now notice I did say, how do you suppose? Okay, experimentation.
When they're trying to build something else.
Hey, trying to build something else. The story, and this is all supposition. I mean, anybody could have been thinking, not just Rachel. No restrictions there.
I have like this funny mental image in my head of like this person like next to like a rock, like holding another rock, and like keep like attaching it.
That's,
I know it's totally both.
That's close to the story that I was taught in my graduate classes.
Oh, really?
That some shepherd boy out in Magnesia being a region, had a staff with iron on the end, and he noticed that the iron staff stuck to some rocks. And so, like, wow, there's something cool with these rocks. And people started playing with them. Now, the story is a very questionable origin. It's not like anybody would know who this person would be. It's just a supposition. The first known use of magnets for something like a compass was done by Chinese people. Oh man, I can't remember what it was, like 2000 BC or something. I think there's some recorded record of them having essentially like a compass. They didn't use it as a compass. They didn't use it for guiding themselves. They used it kind of like we don't use in a Ouija board, something to tell the future or help you make a decision. Which one should it be? Spin the little thing and the magnet makes it behave. So magnetism has had some understanding for a long time. Scientific understanding has been very slow with magnetism. Going back, just a few hundred years, the understanding of magnetism was kind of limited and was thought to be, maybe more magic than anything else. And so by experimenting and playing with magnetism, people learn more. And so our intrepid student, Elet, is now going to come up and show you some fun things that she can do with magnets. I have to change. It's all over there. Just go ahead and roll it out here and then start showing off your mad skills. And meanwhile, I'll be the videographer to make sure that Elet is, well documented. Come closer so you can hear her.
Oh, okay. So, what I'm going to do is, we are going to take these lovely
First play with the compass.
compass. All right.
And you'll probably want to move the compass away from all the other magnets so it can behave on its own. No, I mean away, like physically bring it over there. Because as long as you're close to these other magnets, they're going to affect it.
Okay. So now, put the compass here. Could we all tell where north faces and where south faces, the directions they're in? Okay. So now, if we take this and we move it over here, and sorry, I don't know which side is which. Okay. So if we put the north side down in this one, like this, and then we attach it to where they're both touching.
And then she presses a button.
Yes, and then we take it out, and we put it back over here. Let's see what we notice. Is that it turns to where we want to stop.
No, you did.
And it should stop,
Yeah.
right?
Well, it takes a while, so you
Okay.
got to slow her down. Because there's not much friction. That's the goal of the compass, is so it can rotate without
Yes.
much friction.
So what that does is it changes the forces of so the south end becomes the north end, and the north end becomes the south end because it changes the magnetic.
What you should have noticed here is before it was the red one that was pointing to the back of the classroom. Now it's the blue one.
Yes, and it's because these are soft.
Magnetically soft.
Yeah, magnetically soft, so they're able to change. And then if we were to come back here, and if we put the north side in this one, is that not? Can I do that?
It says put south in that one. So, well, yeah, that one.
Okay. Put the north side in, and then we do it, and then it will change back. All right.
So now she should have reversed it so it now points the right direction again. We'll see. Good, it is.
Yes.
You can tell by the way it stops and comes around. So she's
And now
made
it's
it
back
back to a
normal.
correctly working compass.
Yay. So now we are going to do the same kind of idea with these.
Actually, just show how it works with the compass. We don't need to.
Okay.
Because they've already seen it once.
If we do the south side going down, we can move it because of the field. We can spin it. Yeah. What else want to do? Oh. Okay. So.
So
it's
just bring it down here. Bring it close enough and it'll stop.
Oh, okay.
Okay, so now which one is the north pole of the compass facing toward?
Oh, I thought it was.
Anyone can answer. You can see on the board up there. So turn your magnet around.
Up. around, like,
Yeah, flip it around.
Oh.
No, just, no.
no? What do
Like,
oh, this way.
yes,
Oh,
like that.
okay. So, opposite. Ta-da!
So what we see there is that the opposites attract, likes repel.
Is there another
Is there what?
question? If you held like one of those if you had two of those magnets you felt like in this kind of like direction, where would it go?
What? I'm sorry, what was the question?
Come up, Keziah. Do it. We have it.
Do you have another one? Of the
Yeah.
magnets?
We have two.
Oh, yeah.
We have more than two, but
Oh, okay. Well. What do you want it?
Out of curiosity. He doesn't know what to do.
it's attracted to both.
Sorry, this is really.
This reminds me of a Robert Frost poem.
What was the poem?
The whole two roads diverged in the other road.
And I took the road less traveled.
And
That's made all the difference. We practiced, you know.
You know.
No, we
That was
didn't.
totally a part of this, right?
Totally.
Okay, so
Okay.
Keziah has had her experimentation there.
And, so are we wanting to do that? Are these the compasses?
Yeah. And once again, take them like out
Over
here.
here. Are these
Just
the ones
dump
that
them
work?
out.
Okay.
It's the different ball. That only has. Okay, let's get the ones that are. Some of these point the wrong direction. They're compasses, but. Uh oh.
Arms, yeah.
I didn't do it.
Whatever I did, I didn't do it.
It's frozen. Okay. It's her arm, but. Okay. Okay.
Okay. So you should be pointing with. Which one's
Look
correct?
at this grid. You glare if you say you like your arm. You glare
Actually,
if
we
you
need
say
to put it on
you
paper.
like your arm.
I glare, yeah.
Oh, the magnet?
We need to put them on paper because you can't see the compasses.
Oh, I see.
Okay, so now she's putting a whole bunch of little compasses around the bar mag so we can see the direction that the compasses point.
Okay. Okay, so now. Trying to find one
So-
that's correct.
She's trying to find one that's correct. Some of them point the right direction, some of them point the wrong direction. They all work as compasses. It's just some will lead you the wrong place.
We want it pointing out of the north.
It's like this one here.
Okay. So like that one.
The key is to notice how the directions of the compasses varies by position. And so we have, the compass will align itself. We saw that the north will point toward the south pole. Well, actually, the compass, let's not get too worried about this. But they will align with the magnetic fields because it's attracted to one and repelled by the other. So we can see that magnetic fields, following a general line, they're pointing in or out of the two ends of the magnet. And then along the sides, they're pointing horizontally. And you can, move them around and see how they differ by position. And so that means that there's magnetic force at a distance.
Oh, you can't even see that.
And that's good enough.
Okay, cool.
Yeah, cool. She's done. Thank you, Keziah. And Elet. Elet's getting the credit for this one, just for the record, not Keziah. Okay, so we saw some interesting things with magnets, things that people discovered by playing around with them. I mean, that's basically what scientists do, right? They play with something, try to figure out how it works. The play may become very sophisticated, but it's still just that. And so we saw basic things here, things like that there are two poles and that we can change them. Now that's pretty bizarre that you can change the magnetic poles, because usually we don't think that we can change them. As we have come to understand magnets better, a magnet behaves pretty much like it has a whole bunch of tiny bar magnets inside of it. So I can take the magnet and break it up into little pieces, and each little piece behaves like a bar magnet. So I might have one with north pointing the direction of the arrow, and my arrows can point different directions. Now if I had a bar that was filled with the magnets, each one just randomly oriented compared to the next one, if we added those all together, the net result would be it would act like no magnet at all. And that's what happens with normal magnetic materials. Normal materials like, let's take, I have a stapler here. This stapler is not going to be attracted to any other piece of metal magnetically. I think we're all pretty clear on that. But that's attracted to magnets. That's attracted to magnets. So this is magnetic material. It works magnetically, but it's not a magnet because it has these little domains, as we call them, randomly aligned. Now, you guys are probably too young to really appreciate that classic TV show MacGyver. But in the TV show MacGyver, there is one episode where somebody drops their key down a storm drain. And MacGyver takes like a tire iron or something, bangs it on something like a fire hydrant, sticks it down there, pulls it up, and the key comes out because it's stuck to it because of magnets. Anybody remember that episode? I rewatched it this past year with my son. You know, I had to show him what good cinema is all about. Now, magnets obviously can pick up magnetic materials. So if I take this magnet and if I... okay, that's magnetic. So I can pick this up, right? This here itself is not a magnet. I should have brought... Actually, back on one of these desks, there's still a piece of a paper clip that was left over unless somebody cleaned it up. Well, yeah, it's from lab. There it is.
The actual paperclip, but a piece of it.
Well, okay, a straightened paper clip. Don't hassle me. This is not acting magnetically, but I can pick it up so it's magnetic. In theory, if I have something like this that's made out of magnetic material but not acting magnetically, if I whack it on something, I can cause realignments of those little domains. Of course, if you just randomly realign them, what are you going to end up with? Yeah, still random, hence no magnet. So, you know, MacGyver, they always said, all the things he do are theoretically possible. You know, exploding pine cones and the like. Well, theoretically, it is possible that if I whack this, they jiggle and suddenly randomly orient to behave magnetically. But in practice, they would never develop any strong enough to measure magnetism by that whack. But could happen. And as I'll show you in a little bit, I will make that little nail into a magnet because I'm just that kind of cool. Yeah, make sure you go home and tell your parents. Tell Darla. He's just that kind of cool. Obviously, only uncool people call themselves cool, just in case anyone's confused. So we have two kinds of poles in magnets. One is called north and one is called south. So if I have a bar magnet, I always label one side north, one side south. If I break the magnet in half, which I'm not going to do today, if I break the magnet in half, what will I have? I'll have two magnets. And what about the poles on those two magnets? Maria is speaking so softly I can't hear her. Apparently intentionally that way. we're flying through these answers. If I were to break it, remember the magnet is made because to make this a permanent magnet, all the little domains are aligned the same direction. That's how you make it a permanent magnet. So if I have all these little domains aligned the same direction throughout and I break it in half, all these domains are like this, all these domains are like this. That's right. I'll still have a north and a south. I'll just have now two smaller magnets. Because the magnetism is made by those little domains, it's impossible to just have a north or just have a south. So there are no magnetic monopoles. A monopole means it's just north or just south. It does not exist. So we've got a few things about magnets now. The opposites, did I write down here? I didn't write it down, but I said it. What was the rule about attraction between the poles of a magnet? Opposites attract, and likes repel. Just like we had with charge. Two poles, just like we have with charge. With charge, we had two magnetic charge or two electric charges. Now we have two magnetic charges. I've got to concentrate for just a minute to open the clicker questions because I realize now I forgot to do that. Now we're good. You can't have a magnetic monopole. Magnets are made by aligning those domains. So now let's go on with the stuff I have written here in my lecture. Oh, I should point out here, James Clerk Maxwell, I always feel compelled to point out, his father was born with the last name of Clerk, but he added the last name Maxwell because of a title that he got from another family, and he added the last name to go with it. So technically you should call him James for the first name and Clerk Maxwell for the last name, because Maxwell was just an addition to his true last name of Clerk. Really, really important to no one, except for possibly me. So our first clicker question, what kind of materials show strong magnetic behavior? I did not fit it right on the page. There's supposed to be an LS on the bottom line. Materials. Materia, yeah, it's not. Okay. All right, everyone's answered. And the answers we got, no one said all materials. Darn, somebody's disappointed that no one made that bad answer. Oh yes, let me change it so you can't see that. That didn't do it, but that will. Boom, now you can't see that. 2 people said all metals. 5 people said some metals, no other materials. And 9 people said some metals and some other materials. Well, this being physics class, of course we test these things. So the first thing is we've seen some materials that do work with magnets. Let's try some others. Piece of plastic. Nada. So it's clearly not all materials. We can throw that one out.
You have to whack it on something.
Okay, all metals.
Sit on the ground.
This here is a metal. No attraction. So not all metals. Now we're left with some metals and no other materials, or some metals and some other materials. The correct answer is, I don't have a way to illustrate this one, some metals and some other materials. There are some materials that are not metals that will have magnetism. Mostly we think of metals, or of magnets as being metals. So what types of materials are magnetic? Typically, come on. Oh, it's the slide after this that says what types of materials are magnetic typically. There are 3 types of magnetism. There is diamagnetism, paramagnetism, and ferromagnetism. I like to think of just like with, something is diametrically opposed. That's what diamagnetism is. Diamagnetism is a repelling magnetic force. Who ever heard of a repelling magnetic force? Okay, I didn't see any hands, so I'm going to go with no one. But diamagnetism is a repelling magnetic force, and it actually exists in all materials. All materials have a repelling magnetic force, a diamagnetism. But it's very, very weak in most materials, so we just don't notice it. Then we have paramagnetism, which is a weak, attractive magnetism. And that's present in materials with unpaired electrons. That's getting into a little deeper physics than we're going to cover in this class. But some materials have paramagnetism. And then ferromagnetism, which is what we think of as magnetism. That's the strong reaction that we can see. Things like where my magnets interact. And ferromagnetism is present in only a small number of elements, and those can be made into ferromagnets. Now, these pictures over here are all illustrating one thing: diamagnetism. Diamagnetism. Water is diamagnetic. That means water actually has a repulsive force from any magnet. And so in the top picture we have a strawberry, which has a large water content, in a strong magnetic field, and it's being levitated because the magnet down below is repelling the strawberry. The next picture is from a video, actually. I'm not showing it in class because I'm trying to get through a lot of stuff. But you can watch the video of this frog being levitated because of paramagnetism. And as far as they could tell, there was no damage whatsoever to the frog. It wasn't hurting the frog. But it's just floating around in space. Then we have Tosonomi, a sumo wrestler, who is standing on a plate that's being levitated magnetically, illustrating that you can get a strong force if you have the right materials. I think that's supposed to be a diamagnetic, although it seems odd that it's diamagnetic. Wow, I'm really off. I hit the wrong button to go forward. Okay, this I believe is going to say the types of materials that are strongly magnetic: iron, cobalt, and nickel. Those are your primary strongly magnetic elements. Now, you guys aren't old enough to go buy cassette tapes so you can make a bootleg copy of your favorite songs on your favorite radio station. But back in the day, you would go buy that cassette tape and it would, say like CR3. And what they were telling you was that they're using, well, in that case it's chromium, which is not shown here, as part of their magnetic media. Those cassette tapes just have a thin layer of gel. Did I mention this before? No, yeah. They have a thin gel in them, and in that gel they impregnate it with little pieces of magnetic material. And so you put a magnet over it, and those pieces can rotate in the gel. You take the magnet away, and they stay that way. And so you record material onto the cassette tape by simply having the tape pass underneath a little right head that can make a strong magnetic field in one of two directions. And it makes the magnetic field and makes those align. And so all of your information, we call it magnetic media because it's stored as the orientation of those little magnetic pieces that are in the gel. Which is why you never want to take a magnetic stripe, like a credit card that has a magnetic stripe, and put it next to a magnet. Because it's going to realign those little magnetic domains and erase whatever was on it. Now that process is still used in your hard drives. Your computer has a hard drive. Unless you have a solid state drive, that hard drive has platins, discs, and on the disc you have a gel, and on that gel, or in that gel, you pregnate with the little magnetic domains, and then you have a right head that will come over and orient them, a read head that will come over and just determine what direction the magnetic domains are. Now, how did we get the names north and south for magnets? It came from looking at the action of the compass, which I've put away now. People found that if I took a magnet and put it just so it balances, it will naturally rotate until it's oriented so one side is facing the geographic north and one side is facing to the geographic south. And so people said, well, this is not rocket science. I'm going to call the side facing north, north, and the side facing south, south. Yeah, really crazy, except for one thing. They never stopped to think that opposites attract. So if the north pole of the magnet is facing the Earth's north pole, what's the magnetic pole of the Earth's north pole? South. So the geographic north pole is the south magnetic pole. And likewise, the geographic south is the north magnetic pole. So we can draw a picture of the Earth. My Earth will be a perfect circle because I can draw perfect circles if I cheat. Yeah, pretty awesome skills. Watch this. I will make the Earth's axis a perfectly straight line. I know, it's going far beyond my skills right there. Yeah. Anything I can do to impress my students, I'll do. That's the bottom line here. I can do that too, but I'm not going to. So here's the Earth's north and south geographic poles. And we have learned that the Earth behaves like a bar magnet. And so if this is the Earth's north geographic pole, which pole is this side of the bar magnet? This is the Earth's geographic north. So this is, up there north of Alaska. That's going to be south, and that's going to be north. From what we saw with Elet's demonstration, with the little compasses all around, if we have a bar magnet, it's going to turn out that any magnet that's placed out here is going to align, and we can draw loops to illustrate the direction that those magnets would point at any location. And so it turns out the arrow is indicating the direction that the north will point. That the Earth's magnetic field close to the Earth looks like my black lines. So it looks like the magnetic field from a bar magnet. And when you're standing out there on the surface of the Earth, now we said the compass points north, but look right there. Not only is it going to be pointing north, it's also going to be pointing down. So we also have a type of compass that's called a dip compass, and you align this so it's pointing north, and then it shows you the direction of the Earth's magnetic field in this location. And so the Earth's magnetic field, at least according to this, is pointing pretty steeply down into the Earth here. So the magnetic field isn't just parallel with the surface of the Earth. Other things that are interesting that I'm not going to have covered in my lecture, so I'm going to say it now. We have a sun out here. The sun also has a strong magnetic field. We can study the sun, and we know that the sun's magnetic field approximately every, 11, 13 years, something in that ballpark. The sun's magnetic field flips. So if you think of it like a bar magnet, it's like this, and then every I can't remember if it's 11 or 13.
It's 11.
It's 11, okay. Every 11 years, that bar magnet flips, which is pretty bizarre, right? Well, the Earth does that too, we believe. How do we believe this? Because of studies that started with people taking ships across the ocean. Once they had their little north seekers, their compasses, they're going across the ocean, and these ship captains are noticing that their compasses are just behaving all wonky. They have stars, they know how to navigate by the stars, and the compass is like changing directions as they're going over the ocean. And they're like, what's going on? So the scientists get involved and come and study. And what scientists have found is, on the ocean floor, whoops, out of space. Well, put a blank slide in here. Wow, I'm going to get through my third slide at very least. Maybe my fourth, because I've done the third already. On the ocean floor, we have rift zones. Now, when I was in high school or college, I read the whole Rift War saga, so whenever I get to this rift zone thing, that's what I think about, and call me crazy. But rift zones are regions where magma comes pushing up between plates of the Earth's crust. The Earth's crust is broken up into little plates, kind of like if you took an egg that was hard-boiled and then dropped it. The shell breaks into pieces. The Earth's covered with pieces like that we call tectonic plates. And in the middle of the ocean, we have these plates meet up. And magma pushes up from below, and when the magma comes up, it is much like Samson pushing those columns out. The magma pushes the ocean floor apart, which is why it's called a rift zone. And so these move out like this because of the magma pushing out. Of course, magma, that's molten rock. When it meets water, what's going to happen to the temperature of the magma? It's going to cool. As it cools, it freezes. As it freezes, little magnetic domains, there's iron in some of this rock, hematite ore. The iron will be frozen with its magnetic alignment, the same as the Earth's magnetic field in that location at that time. And so what the scientists noticed was, as they went out, you should use a different color, they found strips with different magnetic domains, or magnetic directions. And they're symmetric going one side and the other out from the center, out from the rift. So what those show is the Earth's magnetic field during this period of time. We had, for instance, north was at the South Pole. But then we have south here, then north, then south, then north. And it's the same on this side. And so by then using radiometric dating for the rocks, they have calculated when they believe the Earth's magnetic field has switched from the North Pole being south like it currently is to the North Pole being north, and back and forth. And they found that on average, the Earth's magnetic field flips about every 200,000 years. And it's been just about 1 million years since the last flip. So we're way, way overdue for the Earth's magnetic field to flip. And that leads you to a few movies that have played around with the idea of the Earth's magnetic field flipping and what would happen on Earth. Now, I don't expect the magnetic field to flip in a day, a week, even a year. Probably hundreds of years for the process to occur is what I expect. But it would definitely cause some changes because right now we use compasses. Birds apparently have things like little iron filings that they use to determine what direction north is. Bees, by the way, they can detect polarization of light. Coolest thing in the world, that's how they determine where the sun is. And yeah, they use like really cool things. God has created wonderful mysteries in nature that I just can't imagine naturally occurring. But the magnetic fields would change and birds would lose orientation ability if that was their only orientation ability. But I'm pretty sure they have backup ones. Yeah, so like in movie, what is it? I don't know. I don't remember the name of the movie. But in one movie they have the birds suddenly just going crazy and flying into people. And Core? Okay. It's really ridiculous. We don't know exactly what would happen, but we're pretty sure it's not that. But it is, the Earth's magnetic field does change. What makes the Earth's magnetic field? Oh, things I'm clearly not going to get to today. Did somebody just agree with me? I will try to get to it. We'll see. Already talked about this stuff in plenty of detail, so I can skip over actually quite a few slides. Magnetic fields from a magnet. Notice the magnetic field lines. We draw field lines just like we drew electric field lines. But magnetic field lines always make a closed loop. They exit the north of a magnet, they enter the south of a magnet, and then inside the magnet they go back through. So unlike electric field lines, the magnetic field lines always make a closed loop. Notice the electric field lines shown on the right, they start at the positive and end at the negative. They don't loop back. Whereas magnetic field lines do. The reason for the difference is the magnetic monopole idea. We have two charged monopoles, a positive charge and a negative charge. We don't have a magnetic monopole. We don't have just a north charge. North always comes with south. And so that's why the lines have to make loops, because you can't just have a north charge. Now, this is actually similar to what Elet showed us with the little compasses, showing the magnetic fields. You can actually observe them. It's not, you can't see them with your eyes, but you can put something there and see how it responds to see the magnetic field in action. And when I put something like a compass in a magnetic field, there's going to be a torque, the rotational equivalent to force, to make it rotate so that the magnet aligns with the magnetic field. And you clearly saw that action once again with Elet's demonstrations. See, it was a good day to do the demonstration, Elet. That's a picture that's just as poor as mine for drawing the Earth's magnetic field. You notice the the greatly exaggerated difference between the magnetic pole and the Earth's rotational axis. The Earth's magnetic pole is not exactly aligned with the magnetic pole, but it's not off by a huge amount. It does move. The Earth's magnetic pole moves from day to day, from year to year. So, where Admiral Byrd found, here's the North Pole, as far as compass north, it would be quite a bit different today. Let me go forward. I'm going to get there. I'm going to do, here it is. Ørsted's accidental discovery. Okay. Full name, I believe, was Hans Christian Ørsted. So he has the compass here. He has his experiment set up. And one of the things he's doing for his experiment is he has a power supply. So I got to connect my power supply here. And he has the power supply, so the wires, oh, nice job. The wire's running over here by a magnet, or by a compass. And then he turns on the power, turns on the power, and he saw the compass rotate when he turned on the power. Now, my compass was moving a little, so I'm going to do it again, try to have it so it's completely stopped. Okay, so turn on the power, and it rotated. See that? As my teacher in college used to say, see? My students mocked him mercilessly behind his back. I assume you don't do that to your physics instructor. Of course not. So, what Ørsted discovered was that a magnetic current, or a magnetic field, was created by having a current going through a wire. And so, doing some study, he discovered the direction is the direction that you would get if you took your thumb and pointed your thumb the direction the current is going, and then wrap your fingers around the wire. The magnetic fields do loops around the wire in the direction the fingers of your right hand would point if you put your thumb the direction the current's going. So we call this a right hand rule. You can see it in action there. Well, if I take this and make myself a coil of wire. Okay, I'm going to skip over these. There's a bunch of clicker questions. Apparently, I'm going to skip them too. I'm going to skip these because I want to discover how the Earth makes its magnetic field. Come on. I'm probably in the middle of clicker questions, yeah. Kimberly wants to answer all of these. Okay, well, it's not there either. I need to come back to the slide I just skipped over, but I think... Okay, remember I need to go back to slide 18. It's coming. It's coming. Okay, if you make a loop of the wire, then on the inside of the loop, the magnetic field produced by each piece of wire is pointing the same direction. And you get a much stronger magnetic field. And so if you make a whole bunch of loops, okay, it doesn't have a whole bunch of loops here. But if you make a whole bunch of loops, you can make a really strong magnetic field. And if I make a strong magnetic field and I put a piece of iron inside, the magnetic domains of the iron will align to make an even stronger magnetic field. So here I have my non-magnetic nail. I cannot affect this paper clip piece. I'm going to now put current through that wire. If I put current through the wire, I have a coil. According to what I told you, what is going to happen with that coil when I put current through it? It's going to what? Just can't hear. Okay, it's going to become magnetic. It's going to make it behave like a magnet. So let me turn on the power. And look, now I can pick it up. Now what's going to happen when I turn off the power? You saw that it lost some of the strength, but it didn't completely drop. Why is that?
There's still current in the wire.
I'm very glad that she said never mind when I disconnected the wire. There can't be a current if you don't have a complete circuit. So it's not a complete circuit anymore, but there's still some residual magnetism. I've now created a magnetic nail from a non-magnetic nail. How did I do that? Okay, electricity. Or another answer would be magic, but we go with electricity. Yvette.
How long will it be magnetic?
Yvette asked a good question. How long will it be magnetic for? Not very long. By tomorrow it won't be. Because what I've done is I have aligned the magnetic domains in here by putting it in a strong magnetic field. But those magnetic domains will randomly realign over time, making it lose its magnetism. Question?
If you whacked it, would it unalign?
Yes, if I whacked it, it would lose its magnetism much quicker.
Can you do that?
No, because I said it would lose it much quicker. It won't lose it all at once. And so I'll be here for the next 20 minutes whacking. That's not any way to teach class.
That'd be great.
That'd be great. Everyone would be enthralled. He's still hitting the nail. I don't know why. Okay, we only have a few minutes left. Slide 18. I hope. Yes. Here is, the Earth's magnetic field, we believe, is created in that same fashion. We have swirling iron and nickel that's melted in the core of the Earth. Closer in, there's a solid core, but there's a molten core. And so that molten core with the swirling conducting material is making the Earth's magnetic field. In the sun, it's liquid metallic hydrogen that's swirling, making the sun's magnetic field. Here are some sizes of magnetic fields just to give you an idea of strength. So our brains, the magnetic field in our brains is somewhere around 10 to the minus 8 to 10 to the minus 9 Gauss. A Gauss is 1/10,000. 1/10,000th of a Tesla. The Tesla is the standard unit of magnetic field. So the magnetic fields inside our brain are very, very weak. If you were to look at the Earth's magnetic field, it's about half a Gauss. A fairly weak magnetic field, but certainly enough for a compass to register. If you were to go to the Earth's core, it'd be 25 Gauss, so about 500 times stronger. A small iron magnet, something like this, has a magnetic field of around 100 Gauss. So that's about 200 times the strength of the Earth's magnetic field for this little guy right here. And then you can get to the small neodymium iron boron magnets. That's the kind of magnet that I had sticking to my battery in lab, or cell in lab. Those are like 2,000 Gauss. That's a really strong magnet. They're very hard to separate those babies. If you go for an MRI like I had on my knee once, the MRI they use magnets as strong as 70,000 Gauss. Very strong magnets. If you have something like a piece of metal on you, it will attract it strong enough that it might pull it through your body if your body happens to be between you and the magnet. So when you're having an MRI, you have to be free of things that are ferromagnetic, things like iron. Then you get to neutron stars, and you can see some really huge magnetic fields occurring there. All right. Have a great day. I'll see you on Friday.